everyone. Welcome to another episode of Super Math. I am Mr. Calo and I am so excited to dive into today's lesson with you. Whether you are here to learn something new, refresh your skills, or just enjoy some educational content, you're in the right place. In today's session, we're going to explore mathematical language and symbol, breaking it down in a way that's easy to understand and fun to learn. So, grab your notes, get comfortable, and let's get started. First, let us define language. Language is a way of people to communicate using words, sounds, gestures, or writing. It helps us to share thoughts, feelings, and ideas with others. Language can be spoken, written, or signed, and it changes and grows over time. Simply means language is a complex systems of our communication, and it is also characterized by its ability to evolve and adapt over time. In relation to mathematics, it consists of symbols, notation, numbers, and operators that are governed by a set of rules or what we call syntax, similar to natural languages but with more rigid structures. Here down below is a picture of different mathematical symbol used to express mathematical ideas, concepts, and relationship in a precise way. As we said, it consists of symbols, notations, numbers, operators, wherein it is a specialized form of communication in mathematics. Now, let's take a look of its characteristic. Characteristics of mathematical language. So here are the three, which it can be precise, concise, and powerful. Precise when we were able to make very fine distinction. Like for example, you are measuring a piece of wood to cut for a project, and the length of the wood is exactly 2.75 meters. Of course, when cutting the wood for your project, precision is crucial. We know that the length is exactly 2.75 meters, wherein it leaves no room for error. This is similar to being mathematically precise. Every details matters to get the correct result. Concise when we are able to say things briefly. Like for example, you are splitting a pizza between four friends. Each person gets one-fourth of the pizza. Instead of saying, okay, everyone gets an equal part of the pizza, which means you take the pizza and divide it into four equal pieces. You simply say, each person gets one-fourth. These concise expressions quickly and effectively communicates the idea. While powerful when we are able to express complex thoughts with relative s. Like for example, you are baking cookies and need to ensure that the dough rises correctly. If the oven temperature stays at 350 degrees Fahrenheit, the cookies will bake perfectly. This statement is powerful because it sets a specific conditions. Our oven temperature at 350 degrees Fahrenheit guarantees us a desired outcome, wherein it perfectly bake our cookies. It conveys that as long as the condition is met, you can be confident in the result. Similarly, in mathematics, a powerful statement sets clear conditions that lead to predictable and reliable outcomes. Now, we are going to clarify a fundamental concept in mathematical language, the difference between an expression and a sentence. Understanding this distinction is crucial, but because it's form the foundation for how we communicate mathematical ideas. Let's start with expression. In math, an expression is like a phrase in everyday language. It is a combination of numbers, variables, and operators, but it doesn't make a complete statement itself. For example, 2x plus 5 is an expression wherein it tells us something about the relationship between x and the other terms, but it doesn't give us a complete idea or a truth value, wherein it does not make sense because we cannot identify whether a given is true or false. On the other hand, mathematical sentence is a complete thought. It is an equation or an equality that states something defined, and it can be either true or false. And it can be also sometimes true or sometimes false. For instance, 2x plus 5 is equal to 15. So this is a sentence. Here we're saying that when 2x plus 5 is equal to 15, we have or there is a specific truth about our x. So that is expression and sentences. To sum it up, expression, like for example, we have 2 is an expression, 1 plus 1 is an expression, and x plus 1 is also an expression. The key symbol here is the equal sign. Remember, this is an expression because it doesn't say something. It doesn't have a complete thought. While we say that is a sentence, if it is consists of complete thought. Okay, to sum it up, an expression is like a phrase, it's a part of the idea, but it doesn't stand alone. A sentence is like a full statement, it's complete, and it can be evaluated as true or false. It can be also sometimes true and also sometimes false. That is also a sentence. Now let us have with conventions of language. In mathematics, conventions are standardized rules and practices that are widely accepted to ensure clarity and consistency in mathematical communications. So these conventions help mathematicians and students understand and interpret mathematical expressions and statements correctly. Now let's move with this example. We have the verbal phrase, the sum of a number and 9. And to transform it into variable expression, we have n plus 9. So what are our keywords here? The word sum, which is when we heard the word sum, it says something that we need to add something, which is we have a number and 9. And by that number, we set as our variable n. That is why we have right now the n plus 9. Now we have the difference of a number and 21. Remember when we heard word difference, that is the operations of subtraction. So now we have n minus 21. The product of 6 and a number, so that will be 6 times n. The quotient of 48 and a number, so that will be 48 divided by n. Now for our last example, we have 1/3 of a number. So remember, in mathematical language, the word of is implies multiplications. And the word is implies an equal signs. So that's how it is. Okay. Now let's move to the basic concepts, particularly with the topics of sets. Set is a collection of distinct, well-defined objects called elements. There is a fairly simple notations for sets. We simply list each element or member. and that is separated by a comma, and then put some curly brackets around the whole thing. For example, we have a set of even numbers. As we said earlier, this given numbers is called the elements. And we group our numbers using our curly brackets for us to have a set of these even numbers. And now we also have the set of odd numbers, the set of prime numbers. As you can see, each member or each element inside our curly brackets are separated by a comma. Now, for the last example, positive multiples of 3 that are less than 10. Remember, we need to have a set or rewrite a set which is positive multiples of 3. Remember, the number positive multiples of 3, we have 3, 6, 9, 12, 15, 18. But as you can see, it tells here that we have positive multiples of 3, but less than 10. So that is why the only set of numbers that we are going to include here is only the value that are less than 10, which is 3, 6, and 9. So that is set of numbers. Now let's move in the topic of relations. So relations, if you still remember your lesson during your senior high or even junior high, relation is a set of ordered pairs, which is denotes as our variable x, and we have the variable y, which is that is our coordinates. The set of all first components of the ordered pairs is called the domain, which is our variable x in our relation. And the set of all the second components are called the range of the relations, which is denotes our variable y in our coordinates. So remember, in a relation, this is a set of ordered pairs. We have pair number. For example, -2, 5, -1, 0, +2, and we have -3. By this set of numbers, our domain here is -2, -1, and +2, while our range is 5, 0, and -3. Now let's take a look for other example below. We have -1, 0, 0, -3, 2, -3, 3, +3, 0, 4, and 5. So all of this given set of coordinates or paired numbers is called relations. Now, in relations, we have functions, wherein it is a relation for which each value from the set, the first component of ordered pairs is associated with exactly one value from the set of the second components of the ordered pair, wherein we can see in our diagram that is a one-to-one relation. For us to identify if our given set of numbers or given relations is a function or not a functions. Let's take a look by this example. We have -3, and then its coordinate is +3. We have -2, and then his range is -6, -1, and we have -0, 0, 15, and then 1, and then -1. So those numbers that we have here is related by one-to-one relations. As you can see, -3 is coordinates with +3 only, and -2 paired with -6. So if we have a given relation that is one-to-one relation, we will call it as a functions. Now let's take a look for example that is not a functions. Let's take a look for positive 1 below. Positive 1 is paired with negative 0 and positive 15, wherein those numbers of our range is related to one domain. As you can see, our domain is paired to range. So this is not a functions. Okay, I hope that we are clear with that. And let's have with elementary logic. So here in elementary logic, we need to know about propositional logic and propositional variables. Now let's take a look with propositional logic. Propositional logic is a mathematical system for reason about proposition and how they relate to one another. For example, every square is a rhombus or every square is a parallelogram. So by this example, we have two statements connected by our logical connective, which is the word or. Later on, we will have a deep understanding about how we use logical connective in this topic. Now let's take a look with propositional variables. Propositional variables are usually represented as lowercase letters such as P, Q, R, S, etc. So this is like just we have statement and then we are going to let that as our variable P or Q, R, S, or etc. Like for example, every square is a rhombus or every square is parallelogram. As we see right now, we have two statements and then connected by the word or. And then we let P as every square is a rhombus and Q as our every square is a parallelogram. So to denote this as our propositional variables, by letting our P and Q by these two statements connected by or, we use this symbol. Okay, so it is read as P or Q. Okay, let's take a look another example. We use logical connectives if then. So in reading this, if every square is a rhombus, then every square is a parallelogram. So again, we let P every square is a rhombus, our Q is every square is a parallelogram. So to denote this into propositional variables, we have P implies Q, or if P, then Q. So to rewrite this in propositional variables, this is how it like. Okay, so now let us have with deep understanding with logical connectives that we introduced earlier. Logical connectives, these are the symbols or words used in logic to connect statements and form more complex logical expressions. They help in constructing logical arguments and determining the validity of the statement. As you can see, we have conjunction, disjunction, negation, implication or conditional, and we have biconditionals. By those names of our logical connectives, they have symbols that we are going to use for us to identify how we're going to transform that into propositional variables. So remember, for conjunction, we are using and. For disjunction is or. Negation is not. For conditional, if then. And then for biconditional, we have the if and only if. So now let us take a look for this example for conjunction. Conjunction, as we said earlier, we use the word and for their logical connectives, and we use this symbol. Both statements must be true for the whole expression to be true. You need to take note of this, class. Both statement must be true for the whole expression to be true. So for our statement, our first statement, it should be true, and next statement should be true for us, our result for the whole expression to be true. Okay, for example, P and Q. So we let P, that is, it is raining. Q, I have an umbrella. So to transform this into logical proposition, so we have, it is raining and I have an umbrella. Okay, so it is raining, and connect our logical connectives, the word and, I have an umbrella. Now let us have with disjunctions. Disjunctions, we use the word or. And this symbol, it is like a letter V. And for disjunction, at least one of the statement must be true for the whole expression to be true. For example, we have first statement is true, second statement is false, so the result is true. Okay? So let us have with this example, which is P or Q. So we let P, it is raining, and Q is equal to, it is snowing. Into propositional logic, it will become, it is raining or it is snowing. Now let us have with negations. So we are using the statement or the word not for negation, wherein we are going to give the contradictions of its meaning. For example, the statement is false if the original statement is true. If the statement is true, the original statement is false. And that is vice versa. For example, we have negation of P or not P. If our P, it is sunny, transform that into propositional logic, we have, it is not sunny. So that's how we sit. We are going to use these negations. Don't worry, in the latter part of our topic, especially in logic, we will have a deep discussion about this, or about using this conjunction, disjunction, negations, conditional and biconditional. Now, let us just have an introduction about this topic. Now, let's move with conditional. Conditional, we use the word if then, and we use this symbol like an arrow. If the first statement is true, then the second statement must also be true for the whole expression to be true. So that is conditional. So P implies Q. If P, it is raining, Q is equal to the ground is wet. To transform it into propositional logic, we have, if it is raining, then the ground is wet. Okay, I hope we are clear with that. We are using the logical connectives if then. Now let us take a look with biconditional, and we use the word if and only if, and we use this symbol like an arrow vice versa, which is both statements are true or both are false. So they are true together or false together. So P, if and only if Q. So if our P is equal to the light is on and our Q is the switch is off, to transform this into propositional logic, we will have the light is on if and only if the switch is off. Okay? And that's it. That's a wrap for today's lessons on mathematical language and symbol. I hope you found it helpful and informative. If you enjoyed the video, make sure to give it a thumbs up and subscribe to Supermat for more educational content. If you have any questions or topics you'd like to ask to cover, drop a comment below. I'd like to hear it from you. Remember, learning is a journey and every steps count. Keep practicing, stay curious, and I'll see you in the next video. Thanks for watching and have a great day.